Hi guys, and welcome back to another video. Today we're going to be solving a very beautiful combinatorics problem from the 2026 APMO, which was held only a few months ago. And here's the problem. Let n be greater than or equal to 2 be an integer. Let a1, a2, all the way to a2 to the n be the 2 to the n subsets of an n element set in some order. And recall that we have 2 to the n subsets of this because every single element is either in the subset or not in the subset. So two choices for each one, so 2 to the n total. And what we want to prove is that this humongous sum here is greater than or equal to 2 to the n minus 2. Now, this seems super random. Like, how on earth are we supposed to prove something like this? And moreover, how are we supposed to tie it all back? It's like we're going around in a cycle. And this is definitely saying something about how many times these subsets here have a common element. So the common theme for this problem seems to be about common elements. So we want to try visualizing that. And as I said earlier, it seems like we're going around in a cycle. We go from 1 to 2, then 2 to 3, all the way to 2 to the n minus 1 to 2 to the n, and then 2 to the n all the way back to a to the 1. So therefore, it makes sense if we visualize this problem by looking at it on a circle. So now let's try out some of our simple cases. So to start, let's try n equals 2. Then we could have the subsets 0 and then 1, the empty one, and then 0, 1, because we just have two elements. And these can go around the circle in any order. So the empty set could be here, 0 could be here, 1 could be here, and then 0, 1 can be here. Then the size of the intersection of these two sets here, well, that's just 0. This one here is also 0 because they're disjoint. These have no elements in common. But over here, we have that it would be 1 because the element 0 is in common. So we can go ahead and circle that. And this gives 1. And then likewise, we can circle the 1 here, and that gives 1. So therefore, the sum here is equal to 2, which is greater than or equal to 2 to the power of 0, which is 1, because that's 2 to the 2 minus 2. Okay, so the obvious question is, can we do better than this? So I'm going to go ahead and keep the empty set up here, and we can just rearrange the other elements as we need. So as we figured out, if 0, 1 is over here, then this has to be 1, and this has to be 0, and that gives the sum of 2. So we can just assume that the 0, 1 is going to be here. And then we can think that 0 is going to be here, then 1 is here. Then this one here, the size of the intersection is 0. This one here, the size is 0, 0. And then this one over here, we end up getting that 1 is a common element. So that means that the size is 1. And then we get that the entire sum is equal to exactly 1. So we've basically gone through all the cases by considering where 0, 1 is. And this basically solves the n equals 2 case. The intuition from the n equals 2 case will be very important in what follows. So now let's try looking at n equals 3. Then we have this bigger circle, and we have our sets to work with are 0, and then the empty set here, 1, 2, then 0, 1, then 1, 2, then 0, 2, and of course set with all of them. Those are the 8 that we work with. And we want to put them around this circle and prove that the sum we get is greater than or equal to 2 to the 3 minus 1 is equal to 2. So once again, suppose we have our empty set here. Then we know that two sets can go next to it, and then those won't contribute anything to the sum, because as I noted earlier, no set can share a common element with the empty set. But remember what happened with the set 0, 1 earlier. And something similar might happen for 0, 1, 2. So we might want to put 0, 1, 2 up here, actually. Then if we have two elements here, or two sets here, then the size of their intersection with 0, 1, 2, well, it's just going to be the size of that set. For example, if I have 0, 1 here, then the size of the intersection is just the size of 0, 1, because these two elements here are both in common here. So that means that if we get a total contribution of 2 from the 0, 1, 2 and the other one, we end up being done. So we want to kind of minimize the contribution we get from 0, 1, 2. So we can put the empty set here if we want to minimize it. And then suppose we put something like 2 here. Then we have to just continue going around this circle and just play around with it. Now the 2 here, we could try seeing what could go with that. And again, we kind of want to be greedy here and minimize the total amount of contribution we have. So when we have this 2 here, we can have like a contribution of, say, 0. And that means that it has to be like this one. It can't be this one because we already used it. It can be this one, or it can be this one. And because we want to save the smaller subsets for later, because they may be the most useful to us, let's try putting 0, 1 here. And now we're kind of stuck, because if we want to get past 0, 1, then we have to like avoid. If we want to get past 0, 1, we have to choose either this one or this one. But these ones are already used. So there's no way we can really get past 0, 1. But what we can do is minimize the amount of contribution we have from it. So let's go ahead and assume that we put 0 here, because that minimizes the contribution. Then we're going to have another one here. So let me go ahead and cross off the ones we've already used. So we've already used the empty set. We've already used 0. We've already used 2. We've used 0, 1. And of course, we used the big one. So now we want to find the one that minimizes the contribution with 0. And we could choose 0, 2, but that will give a contribution of 1 again. So we want to try avoiding that when possible. And when we do that, we end up getting that we can choose 1, 2, for instance. So 1, 2. Because remember, we want to save the smaller subsets for later. And now finally, the subsets we have left are 1 and 0, 2. Now, these two subsets, because their union is, because their intersection is, because they are disjoint, these two do not contribute anything. So more or less, we're worried about the contribution from each of these guys here to this one here, because the empty set doesn't do anything. So let's go ahead and assume that we put like 1 here and then 0, 2 here. Now, we're hoping that this will end up minimizing the amount of contribution we have. And when we end up doing this, we end up getting, this is 0, 0, 0, 1, because these two are in common. And then 0, and then this is 1. This is 0, and this is 1. So we get a total of 3 in this case. And then we ask the obvious question, can we do better? So if we want to do better, then what we can do is we don't have to try reconstructing the entire circle again, but we can instead try seeing how we can change a small portion of this circle and see if we can do anything better. So for example, we can't really do anything much over here because this is the amount of contribution we're going to get no matter what. So we're trying to minimize the amount of contribution we get over here. So in general, it seems like this area here is going to be our problem. And we want only one contribution from here, because what this problem claims is that the minimum is equal to 2. So we want one of these two to go away. So what if we could make this one go away? Then this 1 here would probably be next to the 0. So let's go ahead and try swapping the 1, 2, and the 0. So we have 0 and then 1, 2. Then note that the contribution from these two is still 1 because the common element is 1 here. And then the common element between these two here, there's none. And now because of the swap, this one decreases by 1. And therefore, we end up getting that the total sum is equal to 2. And what the problem statement claims is that we can't really do better. So let's see what's so special about this equality case. And in general, it's always a good idea when looking at such problems to analyze when equality holds, if at all, and what is so special about it. Because whatever method you use to prove your inequality or result, it has to hold in the equality case. Anyhow, we note that 0, 1, 2, and this one here have 0 contribution, and so do these ones here. And when we were talking about 0 contribution, I was saying that we wanted to be as greedy as possible. In other words, this one should be as large as possible without it causing an issue by contributing. So, and the largest such set is called the complement. So this is 2 complement. And then likewise, this is actually 0, 1, 2 complement. And let's see if this is true for the other points on the circle. So 0, 2, and 1, these are also complements. And then we have these two here are also complements. So the point is that we have all these complements here, and any two sets which are complements cannot give any contribution. So really, we only have to worry about the sets which are not complements, and those are a bigger worry. So in reality, we're focused on this one over here, and then this one over here, then this one, or wait, it should be this one here, then this one here, and then finally this one here. So let's see what happened in these cases. So over here, we have a contribution of 1 and a contribution of 1. So that's not super interesting. But over here, we have a contribution of 0. So how exactly do we get a contribution of 0 even if they're not complements? Well, the main idea is really simple, and it is that we weren't as greedy as possible, because we couldn't. And indeed, if we try to use 1, 2 here and be as greedy as we could, then this one would be used twice. So we can't be as greedy as we want to. And therefore, we want to try doing something about greediness. So let's keep this greediness in mind as we progress through the problem. And you may have noticed that I removed the circle here because we're going to be trying doing a general approach. So let's take a look at the sum, and let's try manipulating it in some way with this greediness idea in mind. And we want to somehow turn it into something newer that we can hopefully handle better. And how do we deal with the intersection of two sets? Well, one way to deal with it is by using the principle of inclusion and exclusion. So we could have that this one here is A1 plus A2 minus A1, A2. Now this term here is basically the pesky one, because these ones are actually pretty well controlled. And what do I mean by well controlled? Well, suppose that we sum all of this for all of them, then we get like the sum from I equals 1 to 2n minus 1, where we basically loop around. It is like AI plus AI plus 1 minus that one intersection term. And then, yeah. And we can basically separate this one here out of the sum. And when we do that, we get the sum from I equals 1 to 2 to the n of 8i plus sum from I equals 1 to 2 to the n of ai plus 1, and then minus sum from I equals 1, 2 to the n of ai, and then union ai plus 1. Now this sum here is very, very similar to what we had originally. And we might be able to control these two sums here. Well, we can actually compute these sums exactly, because recall that this one here, because we're just shifting the index, that means that it's just the same sum as that one. So we're really looking at 2 times the sum from I equals 1 to 2 to the n of ai. In other words, the sum of the number of elements of every single subset. Now, this idea of summing over all of them makes us think of like an average. Like, suppose that this was divided by some number 2 to the n, which is the total number of subsets. Then what this is saying is that this quantity here, excluding the 2, is basically the average length of a subset, or the average number of elements in the subset. Well, every single element here has a 1/2 chance of being in that subset. So there's 1/2. So it basically contributes 1/2 of an element if you think about it, because it sometimes contributes 0 elements, sometimes it contributes 1, and it does so half and half of the time. So we end up doing 1/2 times n, which is n over 2, which means that this quantity here is n over 2. And therefore, we've determined that the sum here, by using expected value and not using any complicated sums or anything like that, this is equal to n times 2 to the n over 2. And then when we multiply by the 2 in front, we get that the sum in front is n times 2 to the n. And now we have this 2 to the n here, and we can try combining it into this one, because how else are we supposed to deal with n times 2 to the n? Because this is pretty ugly, and we want to show that it's greater than or equal to this. So if we bring it inside the sum and distribute the n 2 to the n times, we get sum from I equals 1 to n of n minus this intersection term here, ai union ai plus 1. This must be greater than or equal to 2 to the n minus 2. So now let's go back to our circle, because this one here is exactly the same as this one here, but they're also very, very similar in structure, in the sense that this one here focuses on the intersections, while this one here focuses on the unions. So let's see what the contributions from each sum would be equal to. So in this one here, as we determined, we would have a quantity 1, 0, 1, 0, 0, 0, 0, and 0. But for this one here, we end up getting, so let's go ahead and go through it term by term. So the union of these two here is equal to 0, 1, 2. And that means that their union has size 3. And 3 minus 3 is 0. So that's 0. Then now these two, they have union 0, 2, which has size 2. And then 3 minus 2 is equal to 1. I should also list n equals 3 over here. And then over here, we have that 0, 2 and 0, 1 have union 0, 1, 2. So their union has size 3. So we end up getting 0 here. And then these two have union size 2, so that's 1. Union size 3, so that's 0. Union size 3, so that's again 0. And then again 0, and then again 0. So what we end up getting is that this inner sum, the blue one, is equal to the red one as well. Now, the interesting ones here are when both of them are equal to 0. So suppose that we have that both terms are equal to 0. In other words, that ai intersect ai plus 1 has size equal to 0, and then AI union AI plus 1 has size n. Now, because they're the subsets, the only way we can have that this is equal to 0 is if they're disjoint. And then the only way this can happen is if their union is equal to the full set. In other words, they must be complements. So we can basically circle all the complements in this diagram by automatically circling the ones with 0, 0. Now, if we look at all the rest of them, which are not 0, 0, then we see that there's always going to be like a 1 on the outside, a 1 on the inside, or both. But here's the thing. We don't know that there's any 1s on the outside and inside. And in this case, there are no 1s on both outside and inside. It's always either on the outside or either on the inside. And now, how many slots are there that we haven't taken up? Well, there's 1, 2, 3, 4 that are not circled. And out of those, we have that because the two sums are equal to each other, we must have that 4 over 2 equals 2 of them must lie on the outside, and 4 over 2 equals 2 of them lie on the inside, in this maximal case. So therefore, we end up getting that the sum is equal to 2. Now, we might be able to exploit this idea in order to get a solution. So let's go ahead and do this. So suppose we have our 0, 0 contributors, because we want to get rid of those out of the way. Because we want to eliminate those immediately, since they don't do anything. Then those are just the complementary ones. How many of these ones here, these pairs of sets, can be complementary? Well, we saw that there are 4 here. Could there be 5 that are complementary? Well, suppose that we have something like this one is also circled. Then over here, we have that these two are complementary, but then these two are as well. So these two and these two. But because they both complement this one, these must be equal, which is bad. So that one can't be circled. Could this one here be circled? Well, then we have that this one here, these two here complement each other, as do these ones. But then again, these two are the same. In general, if we have 2 consecutive ones which complement each other, we see that we have 2 of these subsets here are the same. So there's no way on earth we can have more than 2 to the n minus 1 total complementing ones. In other words, half of the total number, 2 to the n. So therefore, because these 0, 0s are irrelevant, we have that the total number of, number of 0, 1, where we have 0 on the outside, 1 on the inside. And I should probably make this one red here and this one here blue. And then we have plus the number of ones where we have 1 on the outside and 0 on the inside. And then we have plus the number of ones where we have 1 on the outside, and then we have another 1 on the inside. And we know that this counts all of the ones which are not 0, 0, and there are at most 2 to the n minus 1 of those. So hence this sum here is greater than or equal to 2 to the n minus 1. And what we want to show is that the amount of the red sum here, so we have 1, 0 or 1, 1 in this case. 1, 1 is not in our diagram. We want to prove that the number of 0, 1 plus the number, or it should be 1, 0 because we have red on the outside, plus number of 1, 1 is greater than or equal to 2 to the n minus 2. This is our objective. And we note that the 1, 1 is super, super unnecessary because the number of 1, 1s is just equal to 0. And moreover, because these two sums, we have this one is also equal to number of 0, 1 plus number of 1, 1. And why is this the case? Well, because of this identity we had here. And because they're equal, we end up getting that these two terms are equal. So what we want to show, given that 2 times the number of 0, 1 plus the number of 1, 1 is greater than or equal to 2 to the n minus 1, or it should be, greater than or equal to 2 to the n minus 1, that the number of 0, 1 is greater than or equal to 2 to the n minus 2, or plus the number of 1, 1. So let's think about what the worst case scenario in this equation could be. So what if this one here is equal to 0, just like it was on our circle, which you can look at earlier in the video? Then this one here we know is greater than or equal to 2 to the n minus 1 over 2, which is just 2 to the n minus 2. And therefore it's 2 to the n minus 2 plus 0, and that's 2 to the n minus 2. Okay, so what happens if this one here is equal to 1? Then we know that this one is still greater than or equal to 2 to the n minus 2, and we still get that. So now let's try an interesting case where this one is equal to 2. Then we have this is at least 2 to the n minus 2 minus 1 if you do the math. And then when you add them together, you end up getting 2 to the n minus 2, then plus 1. And that's clearly worse. So really it seems like the worst case scenario is when we have this one here is equal to 0. So let's see if we can do something with that. So let's try solving for the number of 0, 1, because that's what we've been doing. So we end up getting the number of 0, 1 is greater than or equal to 2 to the n minus 1 minus the number of 1, 1 if we solve it all over 2. And when we plug it in, we end up wanting to show 2 to the n minus 1 plus the number of 1, 1, because negative 1/2 plus 1 greater than or equal to 2 to the n minus 2. But then this one here just becomes this one here. And this one is greater than 0. And we are done. So we reduce this to showing that we have I equals 1 to 2 to the n. We have our original one, ai union or intersection ai plus 1 is greater than or equal to 2 to the n minus 2. So then I equals 1 to 2 to the n of n minus ai union ai plus 1 is greater than or equal to 2 to the n minus 2. And this one here counted number of 1, 0 plus number of 1, 1. While this one here counted number of 0, 1 plus number of 1, 1. And because these two were equal, so we're basically using both of these at the same time. And we end up getting that these two are equal. And what we want to show is that because when we have number of 1, 0 plus number of 0, 1 plus number of 1, 1 is greater than or equal to 2 to the n minus 1, then one of these two is at least equal to 2 to the n minus 2. And based on what we were doing earlier, because these are equal, we can add them together. And this is basically what we were doing actually. We were adding them together. And when we do that, we end up getting number of 1, 0 plus number of 0, 1 plus number of 1, 1, or 2 times number of 1, 1. We know that is greater than or equal to this one here, because this one is greater than this one. So it's 2 to the n minus 1 here. It should be 1 here. And because these two sums are equal, we know that it's greater than or equal to this divided by 2, which is equal to 2 to the n minus 2. And that's our solution. And we've solved this beautiful combo problem with basically just this. But the main thing I want you to note is that there's so much underlying motivation behind this solution. And I could have just presented the solution immediately, and that's what a lot of channels would do. But I think that the circle analogy and looking at the equality cases is super, super important when solving this problem. And that's one reason why I absolutely adore this problem. one of my favorite combo problems of all time on my favorites list. So thank you so much for watching this video. Please subscribe if you'd like to see more.